Hello, everyone. Welcome today. This is the first in our Ulteig resource planning series. And today we're going to be focusing upon the fundamentals of the electric grid. This is going to be an extensive series, which we'll go into in just a little bit in terms of all the various topics to be covered. We're certainly not going to be able to do it in 1 or 2 sessions. So we're going to approach it slowly. With that said, I'm going to go ahead and actually jump into our introduction material, and then we will go into the meat and potatoes content soon. So today we're going to go ahead and cover the basics of the electric grid. We're going to get an understanding of what alternating current is, and also provide a high-level overview of three-phase power. You might be an engineer that is already pretty fluent in this. Alternatively, you might be someone brand new to the industry that has really no idea, or maybe, as I say, you're more on the business function side, kind of more on the accounting and finance piece. This material is designed for both. I hope that experienced veterans will get a refresher. And even if you are experienced, I'm amazed over the years how much I learned just by listening. Things I thought I'd mastered, even being in this industry for 20 years, even basic concepts sometimes. Somebody has a better way of explaining it, or just some point of confusion that I thought I understood I didn't. So I hope if you're experienced, you'll get some value to it. And likewise, if you're brand new, we're going to go ahead and go slowly and bring you along. So with that said, I'm going to go ahead and do a quick introduction just to myself, so you have an idea of who you're talking today, who's talking to you today, and what this material is going to be, and that I'm actually qualified to cover it. A little bit about me. Email address is at the top, by the way. It's also going to be in the description of this video below, so you can find it there as well for my contact information. So my name's Andrew Kramer. I have a PhD in physics from Purdue University. My special content or my thesis focused on energy efficiency. I got all the good stuff like general relativity, quantum mechanics, where you look at black holes, all that quantum tunneling, all those discussions like quantum computing, that fundamental physics. But I also knew that I really loved energy and I had a passion for it. And I wanted to go work within industry. So for my doctoral thesis, I chose to focus specifically on energy efficiency. I have about 20 years of experience in research, teaching, and utility planning, focusing upon such fields as fundamental physics, utility resource planning, production cost modeling, integrated resource planning, nodal market analysis, and integrated transmission planning. We'll go over what all of these mean as we go through the series, by the way. My teaching background is pretty extensive. I've taught engineering and as well as fundamental physics courses. And I do a lot of publications as well, so still very active in research. My favorite journals tend to be with the Association of Energy Engineers, AEE. That's where a lot of my recent articles have been published. Just current areas of research interest include integrated transmission and generation planning, as well as benefit analysis surrounding grid enhancements such as GETS and dynamic line rating. One of our most recent papers we're putting out there recently specifically is looking at data centers and the impact on dynamic line rating when pairing with various generation alternatives. So just quickly, this is the one kind of little sales pitch I'll have for the organization. I lead the Ulteig resource planning team, which offers a full range of services ranging from energy market modeling analysis. We'll go over what that means as we go through the course, by the way. This is nodal-based market pricing and curtailment risk assessment, all the way to things like utility integrated resource planning and rate and tariff impact analysis. If you'd like to learn more about these services, I've got my email. Again, it'll be in the area below on this YouTube, or you can find it right here in this presentation. There's my email address, and please add me on LinkedIn, by the way. If you're not certain if we can help you, that's okay. Just send me a note. We can always have a quick half-hour meeting just to talk through things. It doesn't have to be all business either. I love to talk to students and just energy enthusiasts that want to have discussion in the industry. So it doesn't need to, as I say, it doesn't have to be necessarily a business proposition. Feel free to reach out to me, whether you're an energy veteran, just want to talk shop, or maybe, as I say, you're a brand new student, not quite certain, well, is there a spot for me at Ulteig or anywhere in the industry? What are my interests and how might they align? So feel free to reach out. So as we go into resource planning, I'm going to give you a very quick big picture. And then we're going to go into the actual kind of the fundamental physics of the electric grid, which is what we're starting with today. Why resource planning and what is this thing? The discipline of resource planning, as it related to electric power industry, provides engineering and economic-based insight into power generation and system alternatives. Okay, so it's going to help us make decisions of what we want to do and what we don't want to do. The analysis is complicated. It's arguably one of the most complicated things you can do in this industry. It just touches so many different fields, and we will go along this as we go along. It has things such as production profiles for renewables, capital costs for thermal, renewable generation, transmission, all of that's figured in there. Commodity prices, what's the price of coal and natural gas? Even if you're not a proponent of those resources, they certainly are an important part of our electric grid, and we have to take them into account. If you are more on the clean energy side, or even if you're more on the thermal side, you still have to be concerned about emissions. There's requirements from the EPA and other organizations. And maybe, as I say, there might be things like a carbon tax coming into place you have to take into account at some point in the future. So at the end of the day, kind of what we're doing is giving you this picture of what resource planning is. And what it really does at the end of the day is it helps us determine, do we want to build a renewable and storage facility? Do we want to build a thermal generator like a natural gas plant, or maybe a combination of both? It provides the analysis and the numbers to support these conclusions as we go along. We'll go through this in more detail. This is just a very quick big picture before we start going and getting into the specifics. So let's talk a little bit about what we're doing today, which is the basic physics of the electric grid. Again, I'm targeting this so somebody who's brand new can kind of understand it, and then somebody that's experienced you might be able to pick up as well. If you do have that experience, you might do me a favor. If you think I've misstated something, please comment below in the YouTube discussion area. I will be responding. I will also have a LinkedIn post out there. So if you think there's a better way of doing things I missed, or as I say, maybe you're brand new and you forgot something or didn't understand what I was telling or saying, please reach out. I will eventually respond, or someone on the team will respond as well, just in case I'm not available. So let's go ahead and go into the basic physics of the electric grid here. One of probably the most basic concepts is voltage. You're going to hear all about it. It's a term I'm going to use all the time as we go through these discussions. And what is voltage at the end of the day? Really, voltage is the ability to move electric energy. That's what we call it. So we call another term for it's electric potential. It tells us our ability to move charge. Voltage is used to drive electric current. That is the motion of electric charge is current. So you're going to hear all the time terms like voltage and current. For a simple case based upon direct current, we'll go over what direct current is shortly. The amount of current flowing is directly proportional to voltage. So the higher the voltage, the more current I have in my circuit. As a physical example, batteries produce a voltage which can be used to generate a current when connecting the positive and negative ends with a wire or device. So if we want a simple example of a voltage source, I can think of nothing simpler than the typical battery you might buy at a store. You hook a wire up to it, and you will get a current through it, which, again, you can feel in heat. What is the mathematical relationship on this? We're not going to go too crazy on the math in these discussions, but I do have to put down one equation. It's pretty simple. For simple cases involving direct current, electric current is connected to a voltage and modeled with the famous equation known as Ohm's law. And that simply states that the voltage is equal to the current it induces times the resistance in the circuit element. R is known as the resistance. As the name implies, it resists the flow of electric current. The higher resistance, the less current you have flowing in a wire or whatever mechanism you have. R depends upon temperature and other parameters, but for many simple cases, it can be treated as a constant value. So that R value I have listed in that equation above is not actually constant. So I'll just go here with the cursor so we can all see it. This is not actually a constant value, but for many cases, I'd say most cases in your typical engineering application, we treat it as such. Well, let's talk about power consumed, because this relates to the amount of solar we need from the sun, the amount of coal we need to burn, and everything else. The power consumed by a purely resistive circuit element is modeled by the famous equation. Power is equal to the current squared times the resistance, and is also equal to the voltage squared divided by the resistance. You can see from this equation that having larger current leads to more losses than having a larger voltage. The fact that V squared is divided by R is a big deal, rather than and the actual I squared is multiplied by R. The term you're going to hear a lot in the industry is, this is why we are interested in stepping up the voltage. We want to minimize the I squared R losses. This is one of the reasons why we do increase voltage. We'll go over a little bit of that as we go through in terms of when we start talking about power modeling itself on the network. Let's go ahead and go over now an overview of what alternating current is. Our electric system in the United States is based upon alternating current, and there are some very good reasons for that. So I want to give you a feel for this. what this means. Alternating current, also known what I'll be recalling for as AC, is compared to direct current, also known as DC. The United States power grid is based upon alternating rather than direct current. An electric system using alternating current periodically reverses its flow at regular intervals, meaning it goes from maximum to zero and to minimum relative to a reference continuously. This is an example of what it actually looks like as a function of time, how it can go up and down and just swing along. Technically, that means when you look at like the light bulbs in your home, they're turning on and off almost continuously. However, the transition itself is so fast, you really can't notice it. It's 60 cycles in 1 second. So that's pretty fast when you think about it, just on and off 60 times. You might see something occasionally called flicker. That's where you see like the lights flickering. That's actually a different phenomena. If the grid actually slowed down to that level of frequency, it would actually collapse. So that's actually a different phenomena. It's more local as opposed to global. So let's go on why AC, specifically over DC in this case. Conceptually, AC is more complicated than DC. We're going to talk next discussion about a little bit about the history of this whole thing, about why this came to be. It was the genius of Nikola Tesla that pushed AC over DC. This, again, we'll talk about next time, occurred during the so-called War of the Currents, a pretty dramatic name. It was actually a pretty dramatic thing that occurred in terms of the arguments and the industry changing and everything else at the time. We'll talk about this soon. AC, and specifically why it beat out DC, has numerous advantages. They're not apparent at first glance, but when you start talking about power transfer and efficiency, it does make an awful lot of sense. It's easy to, we talked about previously about how we want to get the voltage up to minimize those thermal losses, right? Well, with AC, it's very easy to increase the voltage of transformers. We'll go through that a little bit. Here's an example of a transformer. You basically take a core, and then you wind it on one side, and then you wind it on the other side, the secondary, and then you can step up or step down the voltage, depending on what you want to do with it. AC is nice because it's a natural fit with motors and generators. There are a lot of simplifications you can do with construction when you base them upon AC alternating current. And arguably, both alternating and DC are dangerous. There are arguably some safety improvements in safety with AC over DC. Specifically, as I say, since there is periodic braking for it, if you touch it or get in contact with it, it's maybe a little bit easier to get away from. Both are dangerous, of course. Please don't go, touching any or putting fingers in electrical outlets or anything like that. But again, there are arguably some safety improvements with AC. So now we're going to get a little bit complicated here because we've introduced what alternating current is, and we're going to talk about how the electric system in the United States actually runs, which is on three-phase power. I'm going to be a little counterintuitive here and actually start with three-phase rather than single-phase. A lot of people think, well, one is easier than three. I think it's actually easier to show how three reduces to one. That's just my personal preference for it. The electric grid is based upon three-phase power, which each phase using a separate transmission line to move the power. This is a 150 kV transmission line on the right, and I've got the phases labeled. So each one of these phases is moving power down it. Okay, so as I say that, and that is associated with the quote unquote three-phase. Three-phase power, for each phase of a balanced, and we're going to use that word balanced a lot too, and we'll talk about that just a little bit. Balanced three-phase power system, this shape is the same. So you can think of that analogy we just showed in that picture of the wires. This is what is going on for each one of those wires. They're out of sync with each other. They're all AC swinging up and down, but they're not at the same points at any given time. So the difference is how high or low the shape is at a specific instant in time. Again, remember, they keep moving up and down continuously. One phase could be at maximum, where the others are somewhere between the minimum and maximum. Industrial and commercial facilities often utilize three-phase power directly, where residential applications are normally single phase, or as I say, in this case, it's a single phase transformer with a split secondary. So again, this is kind of the other advantage we see with three-phase. You can actually reduce it down to a single phase. You can split it. You can all do sorts of all fun, crazy things with it that we engineers like to do in terms of when we do design and things along those lines. So let's talk a little bit about the value of three-phase. I think it would be impossible to cover this in just one or two slides. So I'm going to give you a very high-level picture. As we talked about, three-phase has advantages that in generators and motors are easily developed around such systems. In addition, what we call balanced three-phase systems can reduce the cost of wiring. As mentioned, systems can often tap only a single phase, demonstrating the adaptability of three-phase power systems. So again, this is a picture of a three-phase system in terms of an actual diagram. showing the phases, the power sources connected to a impedance source on each end is what's actually going on here. And this is ground or neutral in this case. So now we're going to talk about that word balanced, and it's very important when we talk about three-phase systems. Three-phase power that are balanced can eliminate the return, leading to more efficient power transfer. In balanced three-phase system, there is no power flow down the ground wire. The other thing, and I want to jump back to this picture just real fast here, essentially the power consumed by each of these elements, each one of the phases is the same when the system is balanced. It's a simplification. No system is truly balanced, but for many practical applications, we can think of it as being modeled as such. And it's for a vast majority of your well-behaved power systems, it is going to be approximately balanced and exhibit, and this modeling we do on the balanced systems will accurately reflect it. Now, what happens though is transients, disturbances, and other things, which we'll talk about later, can unbalance the system, leading to uneven power flows between the phases and an energized ground wire. One of the things that occurs in this previous diagram is we can see the neutral/ground wire. In a balanced circuit, there's no power flowing down that line. In a balanced three-phase circuit, there's no power flow going down that line. A lot of times I say, I've had people ask me before, well, there's a ground wire attached to my power pole. Why aren't we losing energy? Why isn't it all just flowing into the ground? Well, the reason is it's a balanced system. In terms of the physics, the way it works out, no power goes down that wire. However, when it's unbalanced, you may get power going down that ground wire that's there. So a lot of times it's supposed to be shielded. I've seen children playing around it and everything else. I try to get them away from there. It's probably okay, but you never can quite be certain. Say theoretically good grounding practice for utilities means it should have a shield around the ground wire. The other thing too is it should have corrosion protection things. You a lot of times see these things breaking off or just like corroding away. So again, you want that there for safety. You want that ground wire there. It's important for the actual safety of the system itself, how it operates. Okay, so we started with three-phase, and now we're going to reduce it to a single phase and go why we might do this and what are we interested in, why we conceptually want to do this. When a three-phase power system is balanced, it can be represented by a single-phase system. In a balanced three-phase system, the power flowing down each of the phases is equal, which allows the simplified single-phase representation. So when you think about it, if I got three wires, three-phase system, and all of them have equal power flows down them, there's no reason why I can't actually reduce it to a single phase. A lot of times what you're doing is a DC direct current approximation of the AC. You have to do, it's not so simple as you just draw a single wire. There's a little bit of math you have to do on the flip side. But it does work out that way, where mathematically you can take the three systems and reduce it to one. The mathematical approximation is a standard assumption of many power flow models, which are interested in longer term forecasts rather than immediate operations concerns, which can lead to unbalanced networks. For my longer term resource planning models, I very rarely get into three-phase discussions. Not to say they're not interesting. It's just we're looking at a 20+ year planning horizon. So, the immediate system impacts of an unbalanced system might be very important for a system protection system relaying group, but for me, it's not quite as interesting. We just assume that that's going to be there for us. And wouldn't be complete if we don't actually show what the famous one-line diagram is. A balanced three-phase system is complicated to draw due to the numbers of lines. We can represent that again as a single line. So we take what would really be three wires and just in a picture form reduce it to one. If you use any of the transmission planning modeling software, a lot of my energy markets modeling simulations, it's all a single phase diagrams that we look at. The famous one-line diagram is a standard representation, and most of your standard software packages that do this kind of modeling are going to have capabilities for it. I should mention one line and one line diagram, just be careful. A lot of times people use them interchangeably in terms of the lingo too. Might get a little confusion on the semantics. We'll try to stay and be careful with the acronyms as we go through this course and define them all. But as I say, it's easy to do. And as I say, the single line diagram is certainly one of those that can bring that up and happen a lot. We're actually complete with this discussion today. I want to try to keep it to maybe 20 to 30 minutes. It's a lot of material we're going to be covering. I'll be recording the next discussion shortly. Hopefully we'll get that online to you soon. And just for what's coming up next, for a little bit of taste of the future here, we're going to actually dive into the history of the electric system, that famous war of the currents. Some on the engineering side, well, why are we interested in this? Let's just skip it and get to the numbers. I don't think you can fully appreciate the numbers unless you see where it came from. And I want to go in through a little bit of the history of it. We'll talk about the World's Fair, Thomas Edison, Nikola Tesla. That even involves a famous story of a serial killer that was on the prowl in New York at the time during the World's Fair, where AC beat out DC. So there's definitely some drama associated with it, and some fun history we'll go through as well. I hope it's entertaining for you as well as we go through. It doesn't have to all be math. Again, I hope you look below, you comment. I'll have a similar discussion thread on LinkedIn. You can find it there, whether it be through LinkedIn or the discussion in the YouTube below. I hope you ask questions, bring up points, bring your own insights. I'll be trying to respond to all those comments. And if you'd like to reach out to me personally, whether it be for a study or just to talk shop, or maybe get some career advice, if I want to get into the energy industry, what should I do? My email address is right there, and again in the section below, or you can add me directly on LinkedIn to go from there. That is it today, my friends. I'm very much looking forward to meeting with you soon and going through the next discussion. So thank you so much, and see you again soon.